Good afternoon, everyone. My name is Łukasz Tychoniec, and I'm an ESO fellow in Garching, Germany. And it's a great pleasure to speak here. Thanks to the organizers for giving me the opportunity. It's the first of its kind of opportunity for me to speak among astrobiologists. So I do hope to give you some observer's approach to how we look into the origins of life on Earth and in the universe in general. A few words on me. I did a master's studies of astronomy in Poznań Observatory, then moved to Leiden for a PhD, and now I'm an ESO fellow. And let's just get to it. So how do we form solar system analogs? So how do we form other stars like Sun and other systems like our solar system? Most of it actually happens within already 10 million years, starting from the collapse. So on the sketch on the right, you can see that we start with pre-stellar core. We move through class 0 and class 1. We call them the protostars stage. And this roughly only takes 500,000 years to conclude this stage. And as you can see on the right, on the left, you have such a young star forming region. This is infrared image of the Perseus molecular cloud, where a lot of interesting stuff happens. There's a lot of energetic radiation. And as we already heard in the previous talk, this radiation can be very important for the development of life. But there are also many other processes that make it a bit difficult to study because they all happen at the same time. So in the earliest stages, we have very powerful outflow, so ejections of material from the protostellar system. There is a lot of inflow because within this 500,000 years, the star needs to accrete most of its matter already. And by the time we reach 500,000 years, most of this material of the cloud that was initially the pre-stellar core is already on the protostar and disk. And from this material, we need to make planets somehow. So as I said, the focus will be on embedded stage, where most of the action happens. And we need to focus on the stage to understand how sun and planets are formed. And the key tool that we use these days as observers to study these youngest stages is submillimeter interferometry. And the two of the facilities I'm using, two of the most powerful ones that we have in this regime, are VLA, so very large array in New Mexico, and ALMA, so Atacama Large Submillimeter Array on the Atacama Desert in Chile. And those tools allow us to deal with the most important, most tricky issues we have when observing young protostars. Because on one hand, as I showed before, those young systems are covered still in their natal envelopes from which they are forming, and it's very difficult to look directly into them. But on the longer wavelengths in the submillimeter regime, the extinction is not such a big problem because the longer wavelengths are less attenuated than the shorter ones. Of course, we need high resolution so we can observe those systems at comparable scales, for example, to solar system. So we need resolution around 50 astronomical units. And the key to solve that is interferometry. So basically combining the information from multiple radio antennas and treating the whole array of telescopes as one huge dish, which would be technically impossible to build, but with interferometry we can actually use them as one giant telescope. Sensitivity is overcome by the amount of dishes we put in, and each of the dish increases our sensitivity so we can look into really faint systems. And by going to deserts, going very high, ALMA is built on a 5-kilometer plateau in Atacama Desert. We can get rid of most of the atmosphere, and we can avoid species like water, which really make it difficult to observe some of those systems. So there are two main ways to observe in the submillimeter regime. One of them is to just look at the continuum, so the thermal emission from protostars. And in the youngest system, as you can see on the right, in the class 0 stage, it's dominated by the black body temperature. So this is the temperature of the system. And most of what we see is actually the dust that is re-emitting the radiation that is absorbed from the central protostar. And that's why we see it only in the longest wavelengths. So those are temperatures corresponding to from 30 to 100 Kelvin if it would be a black body. So we really need to go to longer wavelengths because those stars basically are not emitting anything in the shorter wavelengths. Then in class 1, we get a lot of the whole black body function is moving to shorter wavelengths because the system is getting hotter. But we get a lot of infrared and submillimeter excess due to the remaining envelope and the disk. And at later stages, when the photosphere becomes visible, we see it in even in visible wavelengths, and there's only some residual coming from the disk. So this is one way to do it, just looking at the continuum emission, trying to measure it. The other one is spectroscopy. So at submillimeter wavelengths, we have very rich spectra coming from rotational transitions of different molecules. And actually, molecular complexity is at its peak in the youngest protostars, in that sense that it emits a lot of those molecules. An example of that is seen in this work by Martin Verhelder, where he studied one of the protostars, Perseus B1c, and we can see species like methyl formate, acetaldehyde, and all the others, basically the building blocks of richer prebiotic molecules that are present in the gas phase. And at the later stages, when system cools down a bit, it becomes difficult to observe them because they are frozen on the ice. So first of all, I'm going to very quickly say something about the research I've done in the past on the dust emission from the continuum, because I think it's of very importance and also makes helps us understand a bit more why we need to look at those very early stages. So in the continuum, as I said, we're looking at dust, and on the left you can see beautiful images from ALMA at 1.3 millimeter, which shows the emission from the sub-millimeter size dust grains, which are concentrating close to the protostar's core. And using both ALMA and VLA, we obtain reliable spectral energy distribution at longer wavelengths. And from this, we try to infer what is the total mass of the emitting dust. And this brought us to a very interesting conclusion, because what we showed here on the plot, in the shaded areas in red and blue, are the protostellar spread of protostellar disk masses. And in class 2, we can see median of class 2 disk masses, so the older ones. And in the black dots, we can see the masses of exoplanetary systems. To date, we observed thousands of them with Kepler and other missions, and it's clear that while class 0 and 1 systems, so the very young systems, can have comparable masses to those exoplanetary systems, in class 2 there's way too little mass to actually make even a single gas giant core, for example. So this was one of the important evidences that we provided that planet formation likely start in this young embedded phase in the class 0 and class 1 systems. So again, first 500,000 years, that's already when we need to start making planets. And why is this important? This is because the conditions at those stage then are the conditions of the start of the planet forming stage. And as in the work by Merel van Hoff in 2020, she showed that in the younger stages, the disks are much warmer than the later stages. What we see in this plot is the temperature of the midplane, so the inner regions of the disk, as a function of radii. And we can see that the youngest systems, the temperature is very high up to a very large distances, while in the older systems, such as TW Hydra in class 2, the temperature drops very rapidly. And the temperature here in 20 Kelvin is highlighted as the sea of snow line, so the temperature below which carbon monoxide is frozen on the grains. So because we need to look earlier for the first steps of planet formation, we're also looking at different physical conditions where a lot of species such as CO can be still in the gas phase. But now I'm going to move to actually the spectroscopic study of systems, because I hope I convinced you by now that protostellar stage is very crucial to observe. And in protostellar stage, a lot of things happen at the same time. So we have jet being ejected from a protostar. It carries a lot of the envelope material we call entrained outflow with it. On the side, we have cavity walls, which are the zone where a lot of UV radiation can penetrate without being obstructed by the envelope because the outflow just cleared it out. On this side, we have cold envelope, which is still in falling. There's a disk forming. And in the center region, we have cold core, where the temperature is high enough to show a lot of gas species. And before interferometry, all of this was captured in a single beam of telescope. But now with ALMA, we can actually decompose the systems at the solar system scale, so approximately 50 AU. So our key goal of the study was to use observations of different chemical traces of ALMA to map the kinematics and physics of the protostellar systems. And to achieve this goal, we did a survey of 16 class 0 and 1 protostars in 3 different ALMA bands, so at different wavelengths and at differing resolutions from 0.4 to 6 arc seconds, so corresponding from up to 50 AU to few thousand AU at the distance to the nearby regions, so really covering different spatial scales of those systems. And what's also interesting, and I'll come back to this later, 12 of those systems are actually included in the James Webb Space Telescope guaranteed time observations, which will be already taken next year. So we're really setting the ground for the next facilities that are going to be launched very soon. But now for the results of the study. What we provided, this is the key result of the work, we provided a chemical map which shows which physical components are traced by which different molecules. And of course, there's no time to discuss all this in detail. Feel free to check out the paper for that. And now I will just highlight a few that I think would be of interest for the purposes of this conference. So the first component I want to look at is warm inner envelope, which is highlighted by this area here. This is the region where the temperature gets really high because it's close to the protostar. And because of that, we observe a lot of species in the gas phase. And just to provide a bit of context, in the study in 2019, Maria Drozdowska have compared the abundances in the hot core, in one of those hot cores in protostars, which you see in y-axis as relative to the methanol, with the abundances observed in the comet 67P Churyumov-Gerasimenko, where Rosetta mission went and actually probed the ices directly. And we see that we achieve a very good comparison between the gas phase abundances in young systems and ice phase in the comets. So basically the remnants of the young systems, which probably carry the pristine material from which the star and the planets were formed. So it seems that observing gas phase in the early stages is very important to pinpoint what chemical equipment, what chemical reservoir we have to make planets. And so in our study, we showed actually quite some chemical diversity. In some systems, we saw the classical tracers, such as ketene or HNCO, and other species which are highlighted in the center of the systems. But actually, in some systems, we didn't see any complex organic molecules, but we saw some of the sulfur species. And in the study, we proposed that such sulfur species can be an interesting alternative to study the innermost regions where we cannot see the complex organic molecules. Another interesting component that I think is very puzzling what we found there is the entrained outflow. So the moving at higher velocities than the envelope, usually on the order of 10 to 20 kilometers per second, material that's being ejected from the protostar, and it represents the material carried with a launch jet. And aside from usual tracers we call carbon monoxide or silicon monoxide, which are usually very abundant in those outflows, but we found actually quite chemically rich material, such as acetaldehyde or methanol. And what this all seems like is that those species are a result of sputtering by shock. So that means that when shock is passing through the cloud, because the outflow is moving at supersonic velocities, a lot of dust grains are colliding with each other, releasing the ice mantle into the gas phase. So that's why we observe them. And motivated by that, we actually decided to compare the abundances in a hot core, so in the closest region to the protostar, with abundances in the outflow. Because in principle, this should be coming from the same dust grains, but in the inner regions, ejected by the high temperature processes, and in the outflow by the sputtering processes. And we found for
2 to 3 minutes.
Yes, yes. And for the case of acetaldehyde and ketene, we found excess of the outflow of these molecules in the outflow compared with the hot core, which might suggest that we actually have high temperature processes in the shock that would enhance the abundances of those molecules. And I think those studies where we can compare directly what's happening in the shock with what's happening on the protostar can be of very important to disentangle what processes are triggering the formation of those molecules. Another component is cavity walls. I will just jump very quickly through it, but I think it's relevant also to the previous talk because the question I asked, I actually had that in mind. So basically, we see some evidence that from the innermost regions, the UV radiation actually alters chemistry in the systems very close to the protostar. So you can see, for example, in this plot on the right, C3H2, so one of the small hydrocarbons that's been enhanced in the cavity walls where the UV light encounters the envelope and releases all of those small hydrocarbons, which are probably related to the production after the CO is being dissociated, and then from atomic carbon and hydrogen, they quickly reform into small hydrocarbons. I'm gonna skip this part for a bit because I do want to speak about this exciting project, so James Webb Space Telescope, which will be launched likely in December later this year. And one of the key themes of this is telescope is birth of planets and protoplanetary systems. So I've been specifically involved in the mid-infrared instrument, so MIRI, as a part of the European consortium, which helped build the instrument. And MIRI is going to be really excellent to study protostars because it observes in the longest regime of all the James Webb telescopes, and it's going to be an extreme improvement in terms of spatial resolution. Because before, infrared telescopes could observe at several arcseconds. Now we really get a comparable resolution to what we have already with ALMA. And that's why it was very important to pinpoint those different components with ALMA, because ALMA has one major advantage over James Webb. It has much better spectral resolution, which means that kinematic processes we can study with ALMA with a fraction of a kilometer per second. With James Webb, all going to be seen single channel of 100 kilometers per second. Another thing that they will be complementary at is that they will be studying different chemistry. For example, I'm going to focus on this right now. In the hot core, we can study gas phase products with ALMA, but ICES will be studied with James Webb. So let me immediately move to this slide. In this protostar that I already showed before, where you had a gas phase information about those molecules, we already are getting nice laboratory data. This is a study by Jeroen Terwischa van Saltinga, where he found a nice absorption spectra that will be able to find if certain complex organic molecules are present. So it will be for the first time we can directly match the gas and ice phase abundances. So basically a complete reservoir of what organic molecules we have in the earliest stages. And this brings me to my conclusion. I hope I highlighted to you that James Webb and ALMA will deliver really powerful synergy, basically revolutionizing what we know about the earliest stages of star and planet formation. In my previous continuum studies, I showed that planet formation starts early, which again highlights the importance of studying protostars. By looking at the cavity walls, we showed that UV radiation is really important even in low mass protostars. And complex organic molecules are abundant in young systems. But the open question remains, do they survive and get delivered to planets? And with that, I would like to thank you for your attention.
Thank you very much, Łukasz. Really, really interesting talk. So we have time for a quick question. And I was wondering, actually, a very interesting aspect for me is the ultraviolet light that you showed. And can you actually get some of the parameters of the UV light of the spectrum that goes through these regions that you showed? So do you know, is it very hard UV? Is it around or below 200 nanometers or some longer wavelengths?
So at the very short wavelengths, it's very difficult at these stages, basically because of the hundreds of magnitudes of extinction that we get at the very early stage. So what we're doing, we're trying hard to get the best sub-millimeter tracers of those processes. And one of the actually students in Toruń, Agnieszka Mirocha, is working with Agata Karska in Toruń, has been developing a model where they actually can link CN versus HCN. So basically HCN gets dissociated earlier than CN, and therefore it might be sensitive, this ratio might be sensitive to UV radiation. So we've been working on that in order to get some kind of proxy from which we can understand the UV radiation better. So once this is done, we can try to push for a bigger campaign with ALMA to actually study those ratios in detail.
Very interesting. And actually, the molecules that you show, they are always very small. And my understanding has always been it's because it's very difficult to assign these spectra. but does it mean that there are likely much larger molecules in these protoplanetary disks? Is there any hope that in the future, in the coming years, we'll be able to discover larger and larger systems and see how complex they can get in these clouds?
Yes, so that's an interesting point. Actually, in protostars, I think the better example is what Jacobo showed in the previous talk, the TMC1 cloud. This is the very dark. This is still a dark cloud, but we see extreme chemical richness there. Actually, from largest molecules, they for the first time it was narrowed down the first pHs, right? The small pHs that been seen there. So I think this is really the quest for the a bit shorter wavelengths, even in that's a spectrum of, I believe, 30 something gigahertz, where they can see a lot of those rotational transition from large molecules. At the a bit longer wavelengths, it's more difficult because the energy is a bit higher, and not many of those molecules show those strong transition in higher energy levels. So I believe the quest is more for the earlier stages in pre-stellar cores still.
Great, thank you so much. It's really nice to have you here. Apologies for the technical issues, but I really enjoyed it, and I'm sure that the audience enjoyed it as well. Thanks again, and stay with us as long as you like. Get in touch, and we'll move to another speaker.